Okay, so all right, so let's get started. I have started the live stream on YouTube, and I'm going to hit the record button now. Okay, all right. So far, good morning, everybody. So far, what we have been talking about, we've talked about the general idea that quantum states are represented by vectors in some complex vector space that is known as the Hilbert space, and so on. So in the last class, I had started talking about what do you call it? The history of quantum mechanics, how we discovered quantum mechanics. So well, the history of modern physics, as we understand it, starts with Newton and his predecessors, Galileo, Copernicus, Tycho Brahe, and who were trying to give some sort of a description for the behavior of physical systems. And so this behavior of physical systems, people realized, can be described best in mathematical terms, in terms of the motion of certain objects. And so they introduced various tools, various mathematical tools. One of the mathematical tools, for instance, which was introduced, and for this purpose, Newton invented calculus itself, right, was differential equations. So in differential equations, what we know is that if we have a differential equation, then one can solve it either in closed form. So this is an example of a solution in closed form. That means analytically, you have the exact mathematical expression, you can obtain it in terms of some functions. Or if you cannot solve it in closed form, then you can solve it numerically. So numerically means, you have several algorithms, several procedures. You start with some given assumption for the equation, and then you iterate, or you have various approximation schemes, so on. The end result is that you find that the motion of your system can be described as some function of time, let's say. So x is your position. In this case, we're talking about this equation, which is the equation of a simple harmonic oscillator. And the position of this harmonic oscillator as a function of time can be given in closed form. And it takes this general appearance, right? It looks like a sinusoidal wave. Similarly, if you look at, let's say, the motion of a planetary body, it is given by a similar differential equation. Only now, the expression for this force is different. Instead of this minus kx term, which is what we use in Hooke's law, it becomes, the force becomes, is given by Newton's gravitational law. So it's Gm, capital M, big M by times small m by r squared. So when one can solve that equation also, and you get that, planets move in elliptical orbit around another really heavy object and so on. So the point of all of this is that we have this picture where, which is known as determinism. Determinism means that, like, if you know the history or if you know the present configuration of your system, you can predict the future configuration, and you can also predict the past configuration. So the most famous statement of determinism is due to French mathematician Laplace. And Laplace, it is said in some, I think, in some court or something, to some king, the French king. And people tend to become pompous when they're talking in front of kings. especially scientists, because scientists rely on public money to survive and to do their research. So we tend to exaggerate a little bit. So he said that given if there is an entity which knows the positions and velocities of all the particles in the universe at a given time, for such an entity, nothing would be hidden, past, present, or future, right? So it's kind of like saying that there can be you can have complete knowledge about everything that happens in the universe. So that sounds a little presumptuous, a little arrogant, right? Because you think the universe is so big and so vast, and so how is it that anybody can have complete knowledge about it? So this was the state of classical mechanics in the mid 19th century, right? People believed that nature was completely deterministic, but then a lot of different things happened, which quickly changed that. Well, quickly means that over a period of like 60 or 70 years. So it's not that quickly, but So what were these various changes? Well, one of them was the fact that there was this gentleman called Maxwell, James Clerk Maxwell, and he came up. So there was this phenomenon of electricity and magnetism, and all these different people were studying it, right? Faraday, Ampere, Coulomb, Biot-Savart, Volta. All of these people had been studying how charged objects and electrically and magnetically charged objects behave. And they had come up with a different set of laws, right? So there was Ampere's law, there was Faraday's law, there was Coulomb's law, and so on. And there was Gauss's law. But all of these were sort of separate. They describe different aspects. Then this gentleman called Maxwell, he looked at the whole picture and he said, well, if you use this description of the electric and magnetic fields as some three-dimensional vectors, let's say, E and B, then one can write down a set of 4 equations, right? And I think you have seen all of these equations in your introductory physics courses, right? So one of these equations, for instance, is the statement of Gauss's law that if you have some charge density rho, right, then the divergence of the electric field is equal to the charge density. Then you have the Gauss's law for magnetism, which says that there are no magnetic monopoles. Then you have one law for the curl of the electric field, and this is equal to minus the time derivative of the magnetic field. And you have another law. So this one is known as Ampere's law, and this last one is known as Faraday's law. So there is some coefficient of proportionality, and then one more term is there, mu naught J, where J is some current, some electrical current. So this term is known as the displacement current and all that. So now what was the effect of all of these equations? Right? The effect of these equations is that they tell us that there are some oscillations in of some fields, and we don't exactly know what these fields are. Right? It's a very abstract sort of thing. It's like magic, right? It's like there is something present. We can't see it, we can't feel it, but it's there, and it's everywhere. And in this stuff, things can happen, right? And we can detect what happens by, for example, putting a charge particle. If you put a charge particle over here, what will happen is when these oscillations go and interact with the charge particle, what will happen is a charge particle will oscillate up and down, right? And as it oscillates up and down, you can put this in a circuit and you can measure the oscillations of this charged particle. This is how an antenna or radio works, right? So you can create these waves in the same way by taking some alternating signal and making a charged particle oscillate up and down. And then when the signal propagates from one side to another circuit can detect it in the same way. But now, and it so turns out that the speed of all of these signals happens to be given by one number, 3 times 10 to the 8 meters per second. And this number is also exactly the same as the speed of light, right? So then people said, okay, well, that tells us that what we view as light are actually these waves. They are Maxwell waves, right? They are waves of this electromagnetic radiation. Now, this was a very important, this was a huge development. Okay, so it had huge consequences for this whole idea of determinism. Okay, and how was that? Well, so there are a couple of other developments that were taking place. One of those developments goes by the name, for example, of Young's double slit experiment. So we will encounter this experiment many times because it is one of the most important experiments in quantum mechanics. But right now, I will discuss this purely in terms of the classical picture. So what is a double slit experiment? It says that, well, if you take some barrier and you cut 2 small openings in this barrier, and then you have a screen that is sitting some distance from the barrier, and then you have some light source. And this is ideally this should be a coherent light source. That means it should be monochromatic, and the waves emitted from this should be in phase. So what happens is that these waves, they travel from this light source towards the screen, towards this obstacle. Now, some of the waves manage to pass through, not all the waves, but some of the waves manage to pass through the openings in this barrier. And then here we have a screen. So this, for example, can be of some photographic material can be on the screen. So whenever any light falls on this screen, what happens is that you have some silver, some chemicals are used for photographic processing. They are light sensitive chemicals. When light falls on them, the structure changes, and when the structure changes, you can see it on the screen. So these materials, these silver compounds, they register the presence of light, right? This is the basis of photography, or at least it used to be the basis of photography. Nowadays, of course, everybody has a camera, and inside a camera, there's a different technology which goes by the name of CCD, which is charge coupled device. So that's a solid state technology. So what was found is that when you looked at this screen, what was found is that one would think that, well, if some light passes through one barrier like this, and some other light passes through this barrier, one would think that on the screen you would observe 2 bright spots, one bright spot here and one bright spot here. So if you look at the screen from a different angle, it would look like this. There would be one bright line over here and another bright line over here. But now what was actually observed is that if you have this screen, then what do you get? You get in the central region, you get a bright central region. Then you get a region of darkness or less bright. Then you get another region. So you get these different, you get these so this is dark, right? So you get these regions of dark light, dark light. And if you look at this this diagram and you make a plot of the intensity of light. So if you make a plot of the intensity of light, what you find is that, for instance, in this central region, the intensity is a maximum. Then it drops down, then it again increases, then drops and then increases. So like this. So you get these peaks and valleys, right? And then you have all these different equations which people discovered, which describe these different valleys. So there is Bragg's law, which goes, which is used for in similar phenomenon, but known as diffraction. And it tells you, for example, that n lambda is equal to d sine theta and so on. All these expressions you have seen before, I think. So what is going on here is a phenomenon which is known as interference. Okay, and interference is a signature of wave mechanics. It's a signature of wave phenomenon. Right. So what is happening is that waves are coming out from these two openings in the barrier. There are two openings, right? There's this one and there's this one. And these two waves, when they fall on the screen, so you will get different waves coming from different regions. So for instance, when you look at the central point, you'll see a wave that comes from the first opening in the barrier. And then you will see a wave that comes from the second opening. And what will happen is these two waves over here, they will combine with each other. They will undergo interference. And if the waves are in phase, you get constructive interference and destructive interference if they are out of phase, right? So again, all of this, I think you are all familiar with from your physics, introductory physics course. And so what happens is that you have this interference. This interference tells you that light behaves like a wave. Now that's great. That's wonderful, because we expect that light should behave like a wave, right? That's what Maxwell's theory tells us. Okay. So now this leads to another a problem, right? I mean, so far so good. We are happy. Okay, light is a wave. What does it have to do with determinism? Nothing. I mean, we are still in the realm of classical physics. Everything is good. We are happy. We have waves, we have particles. What's the problem? Well, what happens is that at the same time, people are understanding, are looking at a different aspect of matter. And that is this question of the thermal behavior of matter. Okay. So along with electromagnetism and mechanics, there is a whole different branch of physics that is developing that is known as thermodynamics. Right, and thermodynamics is looking at all sorts of things. It is looking at things such as entropy, work, heat, temperature, right? And then from all of these different quantities, the people working in thermodynamics have found that there are certain equations that a system obeys. So these are called equations of state, right? So an example of an equation of state is what is known as the ideal gas law, right? This is one of the most famous equations of state. You can generalize this to van der Waals law by introducing some interactions between the particles and so on. So what these people in these thermodynamicists are realizing is that, well, if something is hot and if something has a temperature, then where does this temperature come from, right? The question is, where does this temperature come from? So I have a piece of metal, let's say, okay, and I heat it up. I apply some heat. What happens? Well, if you heat it up enough, what you find is that eventually the metal starts emitting some heat, right? More specifically, if you heat it up enough, what you find is that it will start emitting light. That light is actually visible to your eye, right? It has to be quite hot to do that, but it's visible. And when it's visible, so what is happening is that some hot object, this is your hot object, whatever it is emitting radiation. Okay. And what is this radiation? Well, we know that radiation is given by Maxwell waves, right? And so Maxwell waves are being emitted. Now, where did these Maxwell waves come from? I didn't introduce any electromagnetic fields into the picture, right? I just had a heat source, like a fire or something, and I just heated up this object, and now this object is releasing Maxwell waves. So these Maxwell waves can only be generated if there are some charged particles that are moving around, right? This is what we know from Maxwell's theory. So that means there must be some charged particles. Maybe they could be positively charged, maybe they could be negatively charged, and they are moving around. And then what we have is this picture of kinetic theory of heat, right? So the kinetic theory of heat tells us that the heat of an object, the temperature of an object, the heat content is due to the motion of all these different particles which make up that object. Okay. Now you have to keep in mind that when all of these ideas were being developed in the middle and the second half of the 19th century, people still did not believe in the existence of atoms. Okay, so there was no complete logical proof of the existence of atoms. So, but what thermodynamics was telling people is that thermodynamics was telling people that, well, all of this heat and entropy and all, it can only exist if matter has an atomic structure, right? And if this atomic structure, if this structure happens to contain charges, so there are charged particles within this atomic structure, and these charged particles, they move around, and when they move around fast enough, they will release electromagnetic radiation. This radiation will become visible to us. And this radiation, this phenomenon goes by the name of Blackbody radiation. Okay. So now, so what we have is, we have Maxwell theory, which tells us that light is a wave. Then we have thermodynamics, which tells us that matter consists of atomic particles. And when you combine both of these together, they tell you that matter consists of charged particles which are very small charged atomic structure of matter, right? So now when you look at the radiation of coming from a black body, what can you do with it? Well, one of the things you can do with it is you can study the spectrum of this radiation. So what is the spectrum? If you take light, if you take any light, mixed light, then it turns out that you can take an object which is known as a prism, and what happens in this prism is that this light gets broken up into different wavelengths. So for instance, if you send in white light, some mixture of different, not monochromatic light, it will get broken up into light of different wavelengths, where this will be, let's say, red, and then this will be green, and this will be blue. So now what people said is that, well, let's take a black body, let me analyze this radiation, let me see how much is red, how much is green, how much is blue, so on. And how do you characterize red, green, and blue? You characterize it in terms of wavelength, right? So light of a certain wave is red, light of a certain wavelength is green, and so on. Then you can ask how much of each wavelength is there in the light. And what people found is that the distribution of energy in light coming from a black body has this kind of a graph. So for small wavelengths and for large wavelengths, the total amount of energy in the light is 0. Okay, but most of the energy is to be found. So there is some mean wavelength or some maximum wavelength at which there is maximum amount of light emitted, and within this region, most of the energy of the radiation is contained. Okay, great. So now what people try to do is they try to understand how this comes about. Okay. Now, anyways, I've been going on for a long time, so maybe people have questions at this point, or is it just want to take a break from hearing me talk? Maybe. Any questions? No questions? Is everybody still there? Can somebody say something so that
yes,
I'll be
sir.
like, okay.
Yes, sir.
Yes, sir. Okay, good. If you're falling sleepy, you just let me know, okay? All of this might be, you might already know all of this, but not everybody maybe might know it. So. Now, so we have this atomic structure of matter, right? This atomic structure of matter was, this leads to this question of black body radiation. And the question of black body radiation, now, again, I don't want to go into too many details because most of you have seen all of this before. There is something known as, what was the name, man, of these people? Rayleigh, what was that? Somebody tell me that line you get, right? Completely blanking out right now.
Rayleigh-Jeans something.
That's right, Rayleigh-Jeans. Thank you very much. So what Rayleigh and Jeans predicted was that if you look at this spectrum as a function of the, so now this graph was in terms of the wavelength. I can look at the same spectrum in terms of the frequency. So what they said is that if I look at this spectrum in terms of the frequency, their calculation showed that the energy within the light should keep growing, and it should keep growing as some f to some power, f to some fourth power or something like that. The problem was that this was in complete contradiction with the observation. The observation said that, well, initially there is some growth, but then it levels off. And so Yukta has a question. In classical physics, as the wavelength decreases to 0, we measure the total radiation emitted from a black body reaching infinity, but not in quantum mechanics. No, Yukta, we don't measure the total radiation to be infinity, because so first of all, so let me just answer your first question. First of all, that the energy contained within light is inversely proportional to, not inversely, it's directly proportional to its wavelength, right? It, so, oh, sorry, inversely proportional, whatever. So yeah, Yukta is asking the right. I'll come back to your question, Yukta. Okay, I'll come back to it. So, so this Rayleigh-Jeans predicted this weird behavior of light, okay, of black body radiation. This was resolved by a gentleman named as Planck. And Planck came up with a certain hypothesis where he said that, well, if you look at all the light that is being released by these oscillating charged particles, and you make the assumption that this light can only come in small packets, and each packet has an energy which is given by this relationship. So if you make these assumptions, then what happens is that in the Rayleigh-Jeans equation, you have to make some modification, and that modification gives you the correct black body distribution. So this was the first beginning of quantum theory. Okay. So the word quantum, right, it comes from the Greek word quanta. And as you know, quantity means amount of something, right? So quanta is like a packet. It's like an amount of something. So we would also call this a packet of energy. And so these quanta of energy, so energy comes in these small packets. But now there's a problem, because if you say that energy comes in these small packets, then that is a contradiction. Why is that a contradiction? Because, well, Maxwell is telling you that energy light energy comes in waves, right? So Maxwell is telling you that light comes in waves. And now what is the property of waves? The property of waves is that waves are delocalized, right? A wave is by definition something that is spread out over a large distance. Whereas on the other hand, a quantum is something that is localized. Like if you think about it like this, it's a packet. That means it has a boundary. It has a beginning and an end. It has a certain size, right? It can be big or small, but I know where it begins and where it ends. So there is a conflict between these two notions, right? Can light be, how can light be both delocalized and localized? And because if it's localized, then, well, in that case, how is it that in Young's double slit experiment, we are observing interference, right? Because if light is localized, if it comes in these small packets, then these small packets should pass through these slits. These are my slits. These packets should pass through these slits and just fall on the opposite screen, and they should just make these bright spots in two different places. there shouldn't be any interference there, because I mean, you know, I mean, if something is, if you think of two particles, you think of two stones, they don't interfere with each other, right? You can take two stones and bang them together, they'll collide and bounce off, or they might break, but they won't. There is no sense in which one stone will interfere with the other stone, right? So the thing is that at the end of the 19th century, physics was full of lots of contradictions, right? Then there was another contradiction which came as a result of our understanding of Maxwell's theory again. And what was that? This was something known as the ultraviolet catastrophe. This ultraviolet catastrophe term is also sometimes used for this Rayleigh-Jeans expression, because it's saying that as you go to higher frequencies, the energy in the radiation increases to infinity. And that means that a black body should emit an infinite amount of radiation. And ultraviolet means in higher and higher frequency. There is another understanding of this ultraviolet frequency catastrophe, which is the following. So now people were thinking about this atomic structure of matter, right? And there were different models of what atoms should look like. Somebody said, well, atoms should look like this. There should be positive and negative charges, and they should all be like in some clumped up together. So basically, in terms of our Indian experience, this would be the Laddu model of atomic structure, right? Now, then somebody else suggested, well, no, that is not correct, because what in fact happens, and some of you might remember that it was Ernst Rutherford who conducted these experiments, and what he showed was that, well, all the positive charges are sitting together in a very small place, and all the negative charges are moving around this positive charged center. So this thing is called the nucleus, right? So now this leads to a problem. The problem is that if you have these charged particles, these electrons, and they are moving in circles around this nucleus. So this is, you can call it the planetary model of atomic structure. And according to this planetary model, electrons are moving in circles. Now, what we know, another thing that Maxwell tells us, Maxwell's equations tell us that if you take a charged particle and it moves in a circle, then when it moves in a circle, what will happen is any particle which moves in a circle undergoes some acceleration, right? There's some acceleration, right? What is that acceleration? It's given by V by R. Or let's be more careful about this. The acceleration is V by R. V is, let's say, the velocity in this direction, A is in this direction, right? So this object is undergoing accelerated motion. Whenever an object undergoes a charged particle is accelerated, what happens is that it emits radiation. This is one of the predictions of Maxwell's equations. So now, if this charged particle emits radiation, then its energy should decrease. If its energy decreases, then what will happen? Its velocity will decrease. If its velocity decreases, then the radius of its orbit should decrease. So this should keep happening until the particle slowly or very quickly actually falls into the nucleus, right? So if you take the idea of the atomic, thank you so much, v square by r. So if you take this planetary model seriously, then Maxwell's equations are telling you that the atoms should not be stable. In fact, all atoms should almost instantaneously, electrons should fall into the nucleus and a lot of light should be emitted, and you will be left with, well, we won't be here to see any of it because we will all be gone. So all of these questions, which are all have to do with Maxwell's equations and the stability of matter. Excuse me. Early morning physics class, my bad. Is that all of these things ultimately were resolved by quantum theory. Okay. And so what did quantum theory do? Quantum theory said that, well, atomic orbits or orbitals are quantized, right? Electrons can only orbit in certain fixed radial, in certain trajectories which have a fixed radius. And so it is this quantum property which makes atoms stable. And then what else was there? The quantum theory also explained why light can be described by both particles and waves. And I also should mention that there is, apart from Blackbody radiation, there is also the photoelectric effect. So the photoelectric effect, which tells us that light behaves like a particle. So the quantum theory explained atomic orbitals being quantized. It explained the dual nature of light, right? But then the atomic quantum theory said something really strange. It said that if light can behave as a particle in a wave, then why not matter? So that means that if you look at an electron or a proton or a neutron or something like that, then maybe the proton, so if you look at a proton, for instance, well, we think that the proton is a particle. But what if I perform a double slit experiment with protons? So that means I send in a beam of protons towards my apparatus. What will I see on this other end? Will I see just two spots? Well, what happens is that instead of seeing just two spots, what one actually finds is that you get an interference pattern. And this is pretty crazy because it's telling you that these objects, which you think of as particles, are actually behaving like waves. And the wavelength of a wave is given by something which is known as de Broglie relationship. Okay? And it is this dual nature of matter which proves to be disastrous for determinism. So remember, we started out with the notion that nature is deterministic. If you know the position and velocity of a particle at one point in time, you can predict its motion in the past and in the future. But now what quantum mechanics is telling you is that, well, a particle can behave like a wave. And what is the property of a wave? A wave has a property that it is delocalized. Delocalized means that you cannot fix a precise location for the particle. So if I can't fix a precise location for my particle, then how can I predict its motion before, in the past, and in the future? Right? So now determinism becomes indeterminism. Determinism no longer can be satisfied in this picture. Because if a particle can be a wave, then determinism is not possible in the as it was understood earlier. This was actually best encapsulated by Heisenberg in his statement of something known as the principle of uncertainty. So he said that if you try to measure the position of a particle, then what happens is you can only measure it to some degree of uncertainty, right? You say that the position is x plus minus some error delta x. And if you measure the momentum of the particle, you measure it as momentum plus minus delta p. And what did Heisenberg say? He showed was that if you take the product of these two, if you take delta x times delta p, this product will always be greater than or equal to h by 4 pi. Now, h is a constant, it's a universal constant, it's Planck's constant. What this equation tells me is that if I reduce delta x, if this number becomes small, then this number has to become large, because the product of both of these has to be greater than something, right? So for instance, if I say that the product of A and B is always greater than 200 or something, it's always greater than 10. So now let's say A is equal to 1, then B has to be greater than or equal to 10. But likewise, if A is equal to 10, then B, or if I say that B is equal to 1, then A has to be greater than or equal to 10. Okay. So what this tells you is that if you try to measure the position to some accuracy, you won't know the momentum. If you try to measure the momentum, you won't know the position. And what this does is it destroys the old deterministic view of the world. Instead of determinism, we are left with a new picture, a picture that is based on probabilities. So the world suddenly doesn't become completely mysterious and strange. It doesn't become completely indeterministic. It becomes probabilistic. And so we'll talk more about this in tomorrow's class. So are there any questions for now?
Yes, sir.
Yeah.
Sir, like one page before this, you mentioned that ultraviolet catastrophe.
Mm-hmm.
So, sir, what is so one is the first one you mentioned is where Rayleigh-Jeans law doesn't, you can't.
Who is this person speaking? I can't tell.
So Akash.
Akash, okay, yeah.
So one is the Rayleigh-Jeans law not working at low wavelengths. Oh, you said there's another way where it's used.
So that's the collapse of the atomic structure due to the radiation being emitted by accelerating electrons.
Okay, fine. Okay.
Yeah. Though I think, strictly speaking, the ultraviolet catastrophe refers to the Rayleigh-Jeans expression.
Okay, sir.
Sir, about the dual nature, can we say that light is both a wave and a particle? Is that a right statement?
Yeah, of course, that is the point of duality.
Yeah, like is it at the same time? I mean,
yeah. That is the statement of duality, no?
Okay, so at the same time, it's a
but
wave.
one has to be more precise. One has to be more precise about what you mean by at the same time, right?
I meant like, is it like if you perform an experiment on light, it gets a wave? I mean, like as you said, you conducted 2 experiments. Let's say the Blackbody radiation and the other one, double slit one. One showed the wave nature, other showed the particle nature, right? Like I didn't understand. Like in the end, if you consider it to be a wave and a particle, is there a theory unifying this? Like,
yeah, that theory is known as quantum mechanics.
Okay.
Yeah, that's the. I mean, that's the whole reason that people develop quantum mechanics, because classical mechanics cannot explain this duality. Classical mechanics doesn't have that structure.
Sir.
Yeah.
Sir, now since you said that protons and electrons, those particles also somewhat display wave nature, and from the Maxwell's equations, we say that light is a vibration in that electric and magnetic fields. Is there any analogous fields for those particles, or is it just that we consider them to be dual in nature for particles?
No, that's a very nice question. So what Shashwat is asking, that, well, if you think of light as oscillations in the electromagnetic field, then can you think of particles as oscillations in some field? And the answer is yes. But for that you have to study a lot more.
Okay.
and there is a theory called quantum field theory.
Okay.
And that's exactly what happens, is that you have quantum fields, and oscillations in those quantum fields are what we view as particles.
Okay.
Yeah. Okay. So I'll end it here, because I think other people have classes in different places.
Excuse me, sir.
Yeah.
Is there going to be class tomorrow, considering that there it's been on the academic calendar it says that tomorrow is a holiday?
Oh, really? Why? What happened tomorrow?
Janmashtami.
Oh, is it? Tomorrow is a holiday, huh?
Yes, sir. It says also on the academic calendar.
It says so, huh? Well, I guess I'll have to obey the calendar then, right?
That's up to you, sir.
Unless all of you want to celebrate Janmashtami and then dress up as Krishna Lala and whatever, and then come on